Today I'm going to talk about MRI and specifically MRI of magnetic fields. So how to use the MRI scanner to measure the magnetic field or generate an image of magnetic field. I'm breaking it up into 4 sections and talk a little bit about myself, super brief. And then comes the first part of the talk, which is really very educational. So I now know that about half of you, or maybe 1/3, are MRI experts. So this will be a little bit of a review, but hopefully you'll learn new things or refresh your memories. And for the other half or 2/3, hopefully you'll learn something new about MRI. The second half of the talk is where I'm going to delve into the research that I do on B0 mapping and shimming, and more specifically at the end, a project that some interns recently wrapped up on assessing the accuracy of a commonly used B0 mapping technique to determine whether or not any errors or biases in these B0 maps could impact the outcomes of shimming. Okay, and I'll be doing a little Q&A, quick question to make sure that you're paying attention to me. Okay, so intro and background. Who am I? I was already introduced, so you know who I am. My name is Eva. I'm a prof at Polytechnique in electrical engineering and biomedical engineering. My background is in physics and medical physics. Polytechnique is on the other side of the mountain. It's part of the University of Montreal. I co-direct a lab called NeuroPoly. It's co-directed by 4 PIs, myself, Julien Cohen-Haddad, Benjamin Delinaire, and Nicolas Stikov. So we're all MRI experts, and we each have our own specific area of interest, if you will. All right, on to the MRI basics. So I'm going to go over how you do MRI scanning, how you do MRI, what you need in order to do MR imaging. So the ingredients for MRI scanning. First things first, you need an MRI scanner. So here's the main structural diagram of an MRI scanner. One thing to be maybe central thing to note is that you have a very strong magnetic field in an MRI scanner. So this yellow arrow that you see over there, denoted B0, that's your strong magnetic field, which is ideally perfectly uniform throughout the scanner. In addition to the strong magnetic field, you have a few other elements that are essential for MRI scanning. You have something called a gradient coil. These are actual physical windings, coils, through which you drive currents that generate other magnetic fields that are a lot weaker. And the key part here is they're spatially varying. These are going to allow you to do the imaging part of MRI. In addition to your gradient coils, you have a radio frequency coil. So radio frequency coil is another coil winding through which you drive a current, and it is going to generate an electromagnetic wave at the frequency bandwidth of radio waves. So that's the hardware that you need for MRI scanning. The next ingredient is you need a particle that has a property called spin angular momentum, and it has to be non-zero. So you need to have that in order to do MR imaging. In the human body, you have a lot of water. Water is composed of an oxygen atom and hydrogen atoms. Hydrogen atoms are essentially protons and electrons, and protons have a non-zero spin angular momentum. So their spin angular momentum is equal to 1/2. Now, when you have a particle that has spin angular momentum and charge, this particle is going to give rise to a magnetic moment, which is essentially a small magnetic field. So you can think of these protons as little bar magnets, and that's what the diagram here is trying to illustrate. So they're little tiny magnetic fields. And here, mu denotes the magnetic moment, and we see that it's proportional to the angular momentum of the particle. Next question is, what happens when you put these particles inside a magnetic field, like that of the scanner? Distracting overhead voice. So what happens when you put these particles inside a magnetic field? They are going to feel a torque exerted on them that is going to make them align with the magnetic field. They're not going to, I'm going to wait until it stops. All done. Okay. So the particles are going to feel a torque exerted on them that is going to make them align with the magnetic field. They're not going to align with the magnetic field perfectly. They're actually going to start to precess, so have this rotational moment around the direction of the main magnetic field. So that's what I'm illustrating here with the blue balls. Those are the protons. The little white arrow indicates what direction their magnetic moment or their little magnetic field is pointing in. And they're moving around because they're precessing around the direction of B0, the main magnetic field. They're precessing with a frequency that is proportional to the strength of the main magnetic field. So the stronger it is, the faster they precess. And since they're all lined up in that same direction, if you add up their magnetic moments, it gives rise to a net magnetization. That's what the green vector is. So we've put something inside the MRI scanner. And so we've generated some sort of a signal. It's this net magnetization, and we could measure that signal. We want to measure that signal. So the question now is, how do we measure that signal? We know from Faraday's law that a changing flux in time, a changing magnetic flux in time, can induce a current in a coil. So here we have a net magnetization that's processing around a certain direction. That means there's a magnetic flux that's changing in time. So we could measure something that could induce a current in a coil. So what would happen if we put a coil nearby, say over here? We would have actually a small current induced in that coil because there's a changing magnetic flux in time. However, unfortunately, it would be very low because the change in flux would be very low in this arrangement. So what can we do? What we can do is something that was thought of by some very clever people, is manipulate the orientation of those magnetic moments so that they're not precessing around B0 like this, but precessing around B0 like this. So they're still precessing around B0, but they're doing so by tracing out a circle in what we call the transverse plane, the plane that's perpendicular to B0, which we usually say it's aligned along the Z-axis. So that would generate a changing magnetic flux in time in this coil that is a lot bigger, because you see that magnetization is tracing out a bigger circle. And so the magnetic flux in time is changing a lot more than it was before. So this would work, and it would induce a current in a coil that would be oscillatory, like now I have my mouse. Okay, that would be oscillatory, like you see in this diagram here. The changing flux in time is oscillating because the protons, which I will call, and typically in MRI we call them spins, protons, or magnetic moments. So all those three words are interchangeable. So they're precessing in this transverse plane at the Larmor frequency, that frequency that I showed you in the slide before. And therefore the current that is induced is also going to be oscillating at that same frequency. So how can we get those spins to be precessing in the transverse plane like this? We can turn on another magnetic field that we call the B1 field. This B1 field is part of an electromagnetic wave, right? We know that electromagnetic waves have an electric field and a perpendicular B1 field. So it's part of an electromagnetic wave that is circularly polarized, such that the magnetic field component of this wave is tracing out a circle in the transverse. So in the diagram, you see what that EM wave looks like. And in the picture below, you see the trace of what the magnetic field looks like over time. So if you turn on a wave like this, that has the same frequency as the frequency of precession of your dipole moments, of your spins, that will make the spins line up with this B1 field. So they will then too trace out a circle in the transverse plane. So now you have them in the arrangement that you want them in order to induce a significant current in that nearby coil. So we call this process excitation. You excite the spins into the transverse plane. Once you've done that, you don't keep that B1 field turned on, you turn it off. If you turn it off, the spins are going to want to now realign back with B0. If they realign back with B0, you're no longer going to measure a current in that coil. So your current's going to decrease, and it's going to do so exponentially. Okay, so here on the right, we have some graphs showing that signal decrease that is exponential. So here we have the signal that we would measure in this coil decreasing exponentially. We've removed the oscillatory part of it, so we just see the exponential decrease. The signal is going to decrease exponentially with a characteristic decay time called T2. If the magnetic field environment of your spins is not homogeneous, then that signal is going to decrease at an accelerated rate, characterized by a time T2 star. This is happening because the spins are realigning with B0. So the magnetization along the Z-axis, where B0 is pointing, is going to recover, and it's going to do so exponentially as well. That's what I'm showing over here in blue. We see that magnetization along the Z-axis is going to recover, It does so exponentially with a characteristic time T1. So these T1, T2, and T2 star times are interesting to measure. We can put someone in the scanner and see how these signals decrease exponentially, measure these T2 times, and they may differ between tissues, so it's interesting information. So next, I'm going to go into the physical processes that lead to the differences between T2 and T2 star, starting with T2. So T2 is this exponential decrease in the magnetization in the transverse plane. It's happening because magnetization is recovering along the longitudinal plane. So T1 necessarily is contributing to T2, but T2 is smaller than T1. So there's something else that's happening that's making this exponential decay happen at a rate that's faster than T1. So what's happening is something called loss of coherence. We can think of the spins when we tip them into that transverse plane as being in perfect synchrony, like these synchronized swimmers. So initially, when we've tipped them down, they're turning around in perfect synchrony. But over time, they're going to lose synchrony. So we call that loss of coherence. And the reason why that happens is because there are inhomogeneities in the magnetic field at a microscopic scale that are also changing in time. For example, think of these three spins that are existing in your tissue. They're all experiencing the main magnetic field B0, but they're each experiencing the magnetic field of their neighbors because they have a magnetic moment. So we've got one spin on the left, it's experiencing B0, and you've got a spin in the middle that's experiencing B0 plus the little magnetic moment, little magnetic fields of its neighbors. And when I first moved to the slide, you saw they were moving around. So molecules are typically moving around. They vibrate, they rotate, and they move around. So the little magnetic fields that each one of the spins experiences also changes in time as the molecules move around. I said earlier that the frequency of precession is proportional to the magnetic field that the spins experience. This means that each spin is going to precess at a slightly different rate from its neighbors. And this rate could change over time. So then consider the spins when we first tip them into the transverse plane. That's when you can think of them as being synchronized, like the synchronized swimmers. They're all pointing, their legs are pointing in the same direction. If you want to know what the net magnetization is, you take the vector sum of their magnetic moments, and you'll end up with a certain amount. Over time, since they're spinning at slightly different rates, and those rates are changing, they'll lose coherence. They'll start pointing in different directions. And if you take the sum of their magnetic moments now, you'll find that it adds up to something that is lesser than what it was before. So this is what causes this T2 relaxation. It's these randomly fluctuating microscopic field homogeneities. Now let's move on to T2 star. So T2 star happens because of macroscopic field homogeneities. These are field homogeneities that exist on a larger scale, not at a microscopic scale. So for example, think now of three spins placed at different locations. One is experiencing, and I will explain later why these macroscopic field homogeneities exist, but for now, just accept it. One is experiencing a weaker magnetic field, another one a stronger magnetic field. So depending on where they are, they're going to have a different frequency of precession. So same thing as before. Initially, they're all pointing in the same direction. They're in perfect synchrony. Later on, they're going to accumulate different phase differences between them. So they're pointing in different directions. If we add up their net magnetic moments, we're going to get a net magnetization that is smaller than what it was before. So T2 star is caused by the effects of T2 plus the effects of macroscopic field homogeneities, the dephasing or loss of coherence caused by macroscopic field homogeneities. So that is this term here. This term here is due to this effect. Okay, so I've explained what causes T2, what it causes T2 star, and I've mentioned that measuring these values can be useful. It's interesting, but nothing about this relates to imaging. These are not images, they're just signals that come from everywhere in the body. So how from this can we get images? We use a trick called frequency encoding. So I'm going to explain how frequency encoding works in one dimension. The first thing that we need is to use the gradient coils that I talked about earlier. So those are these coils over here we're going to turn them on and we're going to create spatially varying magnetic fields. So we're going to, for the example in one dimension, imagine we're going to turn it on and we're going to create a linearly varying magnetic field along the z-axis. If we do that, then depending on where spins are along the z-axis, they're going to experience, they're going to process at a frequency that is lower or higher, right? Here, so we've turned on a gradient that's a variation of the magnetic field along the z-axis. And here, these arrows represent spins located at different positions along the z-axis. And on the y-axis, we have their frequency. So those that are closer to the origin, that can be the center of the scanner, are processing with a lower frequency. And those that are further along the z-axis are processing with a higher frequency. So here we have an animation showing exactly just that. The blue arrow represents a spin that's closer to the center of the scanner. It's processing at a lower rate. The red arrow is processing at a faster rate. I'll run it again. The diagram's a little bit misleading because they're physically located at the same point in this animation, but in reality, they are not. And that is why they're processing at different rates. So the signals that would be induced in our coil by these spins are going to have different frequencies. The blue spin is going to induce a signal that has a lower frequency. The red spin is going to induce a signal that has a higher frequency. How many blue spins there are is going to determine what the amplitude of the blue signal is. How many red spins there are is going to determine the amplitude of the red signal. What we measure is the sum of all those signals. So we measure the black signal. And what we want to know is from this black signal that we measure, how much is there of each different frequency? So that may sound like something that you've learned in your classes. It's the Fourier transform that's going to tell you that information. So if you take the Fourier transform of your measured signal, you're going to know how much of each frequency is present in your signal. So here it is, the Fourier transform of that black signal. We obtain two peaks. The amplitude of the peak tells you how many protons there are processing at that frequency. The amplitude of the red peak tells you how many protons there are processing at that frequency. And you know what the relationship between frequency and position is because you're the one who turned on the gradient, you know its amplitude. So now you know how many protons or the density of protons, the relative density of protons at each physical location. That is a one-dimensional image. So this is how you can create an image out of this type of data. How do you do this in 2 dimensions? You extend the same principle. There's a slight difference. I'm not going to go into it though. I'm just going to tell you what the signal that you measure looks like, or the model of the signal that you measure. So the signal that you measure looks like this. It's proportional to the density of protons at each physical location in space, and it's got this complex exponential term. The complex exponential has, where's my mouse? I lost my mouse. But the complex exponential has gx, that's a gradient you turn on along the x direction, gy, a gradient you turn on along the y direction. And now we know that by turning on these gradients, we make spins process at different frequencies depending on where they are. Okay, so we're going to do a little substitution here just to clear up our equation. We're going to replace gx of t by this variable called kx, gy of t by a variable called ky, and we finish off with this equation over here. What we are interested from this equation is the density of protons. That if we have a spatial density in terms of space, that's an image. So that's what we're interested in, and this is a signal that we measure. So looking at this equation, we see that this looks a lot like the Fourier transform. So if we want density, we take the inverse Fourier transform of our measured signal. So that's how you generate an MRI image in 2 dimensions. Now the sequence of steps in order to do this is called an MRI sequence. And breaking it down, the first thing that you do is apply that B1 field that I told you about earlier. So that's this RF pulse. It's called an RF pulse because it's a radio frequency wave that is of short duration. So we call it an RF pulse. We turn it on to tip the spins in the transverse plane, and then we turn it off. Then we turn on some gradients for spatial localization. We turn one on along the z-axis, one along the y-axis, and one along the x-axis. And then after a certain amount of time, we measure a signal. So we measure a signal. The model for the measured signal is the one that I've shown you up there. We take the inverse Fourier transform of that measured signal, and we get an image. So we can repeat this again. by waiting a little bit longer after that first RF pulse in order to measure our signals. Measure a signal, measure some signals, take the inverse Fourier transform and get another image. And then we could try it a third time, so get a third image. Now, if we took any given pixel in this image and looked at the evolution of the signal of that pixel over time, we would find that it decays exponentially with a characteristic time called T2 star. So we go back to the exponentially decaying signals that I showed you initially. So disclaimer, for those of you who are experts in MRI, you will have noticed that I have glossed over some steps in the interest of time, but it's enough to follow the rest of the talk. Okay, so that's the conclusion of the first theoretical part of the talk. Quick question here to make sure you're listening. So what causes T2 star decay? A, random fluctuations in the magnetic field that lead to a loss of coherence between spins. B, the recovery of T1. C, large-scale magnetic field variations. D, all of the above. Raise your hand for A. Raise your hand for B. Raise your hand for C. Raise your hand for D. Yay! Good. So that is correct.
Got it.
Yeah, I got it. All right. So we'll move on to B0 mapping and shimming now. Okay, so similar question to before. What happens when you put something in a magnetic field? I've already sort of explained it, but I left out something that is relating to the magnetization. I said you put something in a magnetic field and it becomes magnetized if you have spins with a magnetic moment. But I didn't really talk about how things become magnetized. So things can become magnetized either in a positive or negative way, depending on a property called magnetic susceptibility. So if you put an object that has positive magnetic susceptibility inside a magnetic field, then its net magnetization is going to be pointing along the direction of the external magnetic field. That's what you see in figure A. So in that object, in figure B below, we see that there's a positive offset to the total magnetic field. The total magnetic field being the external magnetic field B0 plus the induced magnetization. So this map here is showing you the offset to the fields. Green is zero offset. So in the background where you have a magnetic field B0, you have zero offset to the magnetic field. Within the object that becomes positively magnetized, you have a positive offset. If the object has negative magnetic susceptibility, the induced magnetic field will point in the opposite direction. So that's what we have in figure C. In figure D, you see the offset field again. So far away from the object, you have zero offset, it's green. Within the object, you have a negative offset to the magnetic field, so it's slightly blue, okay? The key thing that I want you to notice here is that in the object, the magnetic field is uniform. But at the boundary between the object and the surrounding medium, which has its own magnetic susceptibility, there's a strong spatially varying magnetic field. So the magnetic field is inhomogeneous at the boundary between the two objects. So this is something that happens in the human body when you put it inside a scanner. The human body is composed of various tissues. Each one of these tissues has its own magnetic susceptibility. For example, here's a simulation of a human torso. We've got soft tissue, we've got lungs, bone, bone marrow, spinal cord. Each one of these tissue types has its own magnetic susceptibility. Some of them might be positive, some might be negative negative, but different values. So below it, we have a simulation of what the field offset would look like for this particular susceptibility distribution. And we see that at the interface between the tissue types, we have these strong magnetic field homogeneities, just like we did in the simplified spherical object. Now, if we go back to what we learned earlier in the first slides, I told you that if you have macroscopic field homogeneities, this leads to accelerated signal decay, and we call that T2 star. So now I've explained what the source of those macroscopic magnetic field homogeneities is. It's the boundaries between tissues with different magnetic susceptibility. So this occurs everywhere in the body, it occurs in the brain, and here's an example of what can happen if you have very big differences in magnetic susceptibility. We have an image of the brain and a big black spot in the front of the brain. You have that big black spot because the front of the brain is close to the nasal sinuses. Nasal sinuses have air, and there's a very, very big susceptibility difference between air and the surrounding tissue. So you have very strong magnetic field homogeneities that causes accelerated signal decay or loss of coherence of the spins. And it can either accelerate the rate at which your signal decreases, or it accelerates so much that your signal decreases essentially before you can measure it, so you don't measure anything. So this is a problem. Obviously, you don't want your images to look like this. So here I'm just explaining that this is caused by a loss of coherence, like I explained before. So this is a problem. What can you do about it? You can do something called B0 shimming to try to homogenize a magnetic field. The first step to B0 shimming is first knowing what the problem is. So you have to measure the magnetic field to have an idea of what the extent of the field homogeneity is. So how do you measure a magnetic field? You do so by acquiring two images using a sequence similar to what I'm illustrating here on the board. So it's the same kind of sequence that I showed you earlier. And you're going to measure two images, one at time t1 and one at time t2. Each one of these signals that you measure is a complex signal, right? If you remember, I showed you the equation. It's S is proportional to the density, and then there's an complex exponential term. So it's a complex signal. It's got a real and imaginary part, therefore a magnitude and a phase. So here's an example of what a magnitude and a phase image looks like acquired at one point in time. What we're interested here is the phase. So the phase is equal to the frequency of precession times the time at which you measured, plus an initial phase offset term. The frequency of precession, omega, I've already told you, is proportional to the strength of the magnetic field. The strength of the magnetic field, the constant proportionality is this gamma, and the strength of the magnetic field is the main magnetic field, B0, plus an offset term caused by differences in magnetic susceptibility. This is what we're interested in knowing. We want to know what the field offset is. We want a map of that. So what we're going to do is acquire a second image at a later point in time. We're going to take the second phase image and we're going to subtract the two. If you subtract the two, then you cancel off the B0 term and the phi0 term, and you end up with delta B0, a magnetic field map. So this is how you generate a magnetic field map. Here are some examples of what magnetic field maps look like. We have one here in the brain. So we see the red is the strength of the field offset. You see red in the front of the brain. Again, that's because of the nasal sinuses. You also see some offsets to the sides. That's because it's close to the ears. There's also a little bit of air there. Here's another example of the brain, different orientations. And here's an example for the spinal cord. So in the spinal cord, as you approach the lungs, you have some really strong offsets. And you also have offsets that vary periodically, and that's because of the vertebrae. So all of these offsets cause problems in your images, cause signal loss, which you want to correct for. So how do you correct for it? You use, again, the gradient coils that I talked to you about. The gradient coils can create spatially varying magnetic fields. So that's exactly what you want. You know your magnetic field is inhomogeneous, it's spatially varying. You've measured it, you know what it is. Now you want to generate another spatially varying magnetic field that matches exactly that, but of opposite amplitude to cancel, so that you end up with something uniform. So you're going to use your gradient coils for that. Scanners typically come with a few gradient coils, and these gradient coils create spatial harmonic functions. So we have spatial harmonics have various orders, and the gradient coils that are installed will generate the first and second order spherical harmonic functions. So the first order spherical harmonic functions are just linearly varying functions. So linear gradients along X, Y, and Z. And then the second order create shapes that are shown here in this image here. So you're going to generate a field map, and then you're going to try to decompose your field map as a linear combination of these functions, of the second order spherical harmonics and the first order spherical harmonics. So you're going to find the amplitude of each one of the functions, and that amplitude is going to determine what the strength of the current you need to run through that coil is in order to generate that field. So this is something that scanners typically do. It's standardized. Before you acquire an image, the scanner will acquire a very quick B0 map, and it'll do this fit of the B0 map to a sum of spherical harmonics. And this is an example of some results of that. So the scanner has shimmed the magnetic field, and now we've measured the magnetic field just to see what the result of that was. And we see that the result is not too great. There's still some super strong offsets in the front of the brain. So you can do more advanced approaches. This is called global shimming. That's what the scanner does. You can do something a little bit more sophisticated called slice-wise shimming, wherein you would take the B0 map that you measured, and then you would look at one slice at a time. And for each slice, you're going to decompose that slice in terms of a linear combination of spherical harmonics. Instead of doing it for the whole volume, you do it for just one slice at a time. If you do that, you're able to get a much better shimming outcome. So the column here on the right shows the results of shimming on a slice per slice basis. So if you compare the two, it's pretty obvious that this is much better. So these are some results from my lab that one of our students worked on. He also developed a toolbox, a software toolbox that helps you do all of this because it's not so simple. Yeah, that's it. So next part of the talk, last part of the talk, I'm going to show you some results where we try to determine. So some of these field maps, we already know they have some sources of error, some biases, and we try to determine these biases, what is their impact on shimming outcomes? How important are these biases? Should we take them into account, or is it safe to just ignore them? All right, so back to the sequence that we use for measuring the magnetic field. Is a sequence where we acquire images at 2 time points. So here, I want to draw your attention to the gradients that we turn on in order to do imaging. These are gradients that we turn on really quickly. We turn them on and off really quickly. When you turn magnetic fields on and off really quickly, that creates varying magnetic flux that varies in time, right? That is the definition of a varying magnetic flux. So that can induce a current in any coil that is within the scanner. We call those currents eddy currents. Those currents generate a magnetic field as well. So the magnetic field that we measure with a sequence like this is actually the magnetic field due to the susceptibility differences, plus any possible magnetic fields that have been created by eddy currents. So here we have measured B0 map is actually equal to eddy current induced field plus the inhomogeneity due to susceptibility differences. So I'm going to call this B0 map a biased B0 map. So this is something that we already know exists, right? The question now is, how worried should we be about this when we're doing shimming? So one way to answer that question is to acquire first a regular B0 map, our biased B0 map, and then acquire another B0 map with reverse polarity for the encoding gradients. So you see the gradients here have all been reversed, polarities have all been reversed. If the polarities have been reversed, then the induced currents are going to be reversed as well, and the magnitude of the eddy-induced field will be reversed as well. So then we can take both field maps, add them together, take the average, and that should cancel the eddy-induced term. So now we have what I call an unbiased B0 map. So the point of all this is to shim using the biased B0 map, which is what usually the scanner does and everybody does, and to shim using an unbiased B0 map and see whether or not there's a difference between the two. So here are some results of the magnetic field. This is the magnetic field after shimming, first using the regular biased field map, and second using the unbiased field map. So our field map where we cancel the effect of eddy currents. So we do see visibly there's a difference between the two, and the difference is mainly in the front of the brain. So if we look at the distribution, a histogram of the values of field offsets, the different field offsets in different pixels, and that's what I'm showing you here, we see that for the biased field map and the unbiased field map, there's a difference of about 25 hertz, 20 hertz. So that seems significant. But a lot of times when people do shimming research, they determine that, okay, there's a difference between this shimming approach and that shimming approach. But at the end of the day, you want to do shimming so you can get good quality data. You might want to, for example, shim before measuring T2 star. So that's looked at less. So that's what we did, what I'm showing here. So that's what we did. We measured, after shimming with these two techniques, we measured T2 star to determine whether or not this 10 hertz offset difference between the two shimming techniques will have a measurable impact on the T2 star values that we measure. So on the left, I have a map of T2 star in the brain using both shim techniques. So that's on the left over here, using the biased B0 shimming technique and the unbiased B0 shimming technique. On the right is a map of T2 star in white matter, again, using both shimming techniques, biased and unbiased. And here we have an ROI in the front of the brain, the part that was most affected. And I'm showing the exponential decay curve of your signal for both shim techniques. So in blue, we have the unbiased shim, and in orange, we have the biased shim. So we do see that there is a difference, and the difference is about 10 milliseconds, which in my opinion is significant, because if you measure about a 10 millisecond difference in, say, a healthy or unhealthy tissue, then that's enough for you to say that there's something happening causing that change. So this brings me to the end. Here's a list of everybody that is affiliated with our lab, and in bold black, the students that worked on these shimming projects.
Super. Thank you very much. We have time for questions. We can do questions online, either unmute yourself and ask it, or type it into the chat. And of course, in the room, if you write it on a piece of paper and hand it to me, no, say it out loud. Come on. There's a lot of, yes, MR people here, so.
Yeah, a question concerning a global shift. Is there something preventing manufacturers from having region coils that could create third harmonics fields?
At 7T, scanners typically have third order spherical harmonic coils, but a lot of research centers are actually disabling them now because they seem to make things worse. So this,
just for
yeah.
people who online, the question was, let me just repeat the question. It's whether, I didn't totally grasp it.
I can repeat it.
Yeah.
Something preventing manufacturers from having gradient coil systems that can produce third order spherical harmonics fields.
Right. So manufacturers, what prevents them from generating these gradients themselves?
So at 3T, I imagine that when they're manufacturing these shim coils, they've probably done some comparison between up to second order and up to third order. Probably up to third order doesn't do much. When you're shimming, if you've ever been involved in shimming, you know a little bit more about it and how you can manually shim yourself at the scanner. You'll see that the second order spherical harmonics, as you shim and reshim, they tend to vary a lot. It's not a very stable fit. So my best guess is that third order is just doing absolutely nothing. Spherical harmonics are not a perfect fit to the actual physical distribution that's generated by susceptibility differences. It's a perfect fit to a hypothetical ideal scenario where you have an object, I think, an object that has a susceptibility difference with its medium that is perfectly out of the field of view of where you're measuring the field. If I'm not mistaken, that is the theoretical scenario in which you can decompose the magnetic field distribution into a set of spherical harmonics. So that is not exactly what you have in the human body, which explains why you'll never get a perfect fit using spherical harmonics. Yeah.
Great. Other questions? I didn't check and see if there are any in the chat.
I have one.
Oh, go ahead, Jorge.
You showed us for mapping V0, a linear model between the phase and V0. I was wondering if throughout your work, either in V0 shifting or QSM, have you find any motivation to go to another that is not linear?
For field mapping?
Yeah, let's see what those higher order terms do.
No, because our echo spacing is typically really short, or we're trying to have it be as short as possible because you want your B0 acquisition to be as short as possible. So I don't think that would really be necessary. I don't think so.
Good, good. I had a question. Again, I don't know much about MR. You talked about how the susceptibility induced B field inhomogeneities affect T2 star. Does it also affect T1? Or is that more robust?
So I know very little about T1, but I think that you can do T1 with a gradient echo readout or the spin echo readout, depending on the sequence. Maybe some of the students in the audience who do multi-parametric mapping know a little bit better. I think that you can, so T1, you would do an inversion pulse and then let your magnetization recover so that the amount of magnetization is proportional to the T1 recovery time. And then you have to tip your magnetization to the transverse plane to measure it once again. And you could do that simply by applying an RF pulse and reading it out. That would be a gradient echo readout. Or I think that you could apply a 180 pulse and do a spin echo readout. If you did that, then it would be less sensitive to field homogeneities. I'm not sure, like the typical sequences that are used for T1, like MP rage or MP2 rage. Anybody in the audience? Not sure if there's spin echo based sequences or not.
So yeah, it's not just, I guess it's not just the quantity you're measuring, whether it's T2 or T1, but it's also the sequence.
The way that you're measuring it.
Sequence that you're using matters.
Yep.
Cool, thanks. Anyone online?
There's a little question in the chat. I can check what it is. It might just be from earlier saying the sound is good.
Yes,
Yeah,
that is good.
you ready?
I appreciate the didactic slides at the start. I've learned MRI like 10 times in my life and I forget it each time. So thank you for the refresher. Puts us all on the same page at least.
Yeah.
I have an extra question.
Yep.
It's the first time that I see a map for spinal cord.
Mhm.
And you mentioned that the values are very good.
Yeah, yeah. The magnetic field will have offsets that vary periodically along the spinal cord because you have the discs.
Now I wonder, since you're moving into QSM of the spinal cord, how you find that type of value that you will find in the middle will affect the unwrapping that you will need for QSM?
Probably, but we haven't done it yet.
Okay.
I have a follow-up question on the spinal cord. I think we're very used to seeing brain images, but on that spinal cord, field. Can we go back to it and could you just tell us what we're looking at, like what the orientation is, what the scale is?
Yeah. Okay, so the scale, we measure it in hertz. Proportional, so it's proportional to the frequency, or it is the frequency. And around the spinal cord, as you approach the lungs, so at the end of the cervical spine, you typically have about 100 hertz positive or negative offset. So if it's not, the anatomy is not entirely clear, the spinal cord is here. The lungs would be here. Or no, sorry, the lungs are here. No, this is the heart. This is the heart, this is the lungs, this is the spinal cord. And these are kind of subtle, but those are the periodic variations that you see from the discs, spinal cord
Okay,
discs.
so we're seeing quite a big portion of the spine. Or this isn't just one disc, it's several discs.
Yeah, the spinal cord goes from here all the way down to your coccyx.
Okay, nice. I see there is a new chat one. The question is, does the B0 mapping help with the design of coils that may prevent imaging effects close to the ear channels and close to the sinuses?
Let me read the question.
Yeah.
Does B0 mapping help with the design of coils that may prevent imaging close to the ear? Yes, for sure. So if you want to design coils to better shim the brain and specifically like front of the brain and around the ear canals, then you would want to start with field mapping in order to model what your coil design should be. So when you build coils, you're going to have a model of what fields your coils generates, and you want those fields to be canceling what you're measuring with your B0 map. So you definitely need a B0 map. Or, I mean, you could have a simulated B0 map. You can simulate what field offsets you will have in the brain using a susceptibility distribution. So this slide here was a project that I did a few years ago where I simulated the different susceptibilities of different tissues around the spinal cord and then simulated what the magnetic field offset is. So you can do that for any part of the body as long as you have some idea of what the susceptibility values are for the different tissues, which is not that easy to know.
So now I have a question. You showed the results of the comparison of the two sheathing units.
Yeah.
Those were measurements after sheathing or?
Yep.
Okay.
Mhm.
So how was the process of getting the machine to machine, giving the approach.
How was, which process?
The process of measuring everything that you need to do the different shimmy and like feedback that into the machine and ask the machine reaching in this new another way.
Oh, okay, yeah. So you can do that, depending on if you want to do a global shim. If you want to do a global shim, you'll measure a field map. If you want to do it yourself, the scanner already does it, but let's say you don't trust a scanner. They do have algorithms that are a black box. You don't know exactly how they're computing, how they're doing that optimization with the spherical harmonic terms. So if you want to do it yourself, we have software for that. That's the software that Alexandre Dastus, whom I think you said you know, that's what he worked on for his master's. So it's called the Shimming Toolbox, it's somewhere here. Or I thought it was here. Yeah, well, there's a little reference here to his paper. So using our software, you could decompose your field map in terms of the spherical harmonics, and then you get the amplitudes of each spherical harmonic term, and you can input that manually in the scanner. Yeah, was that what your
Yeah.
question was? And if you want to do something more advanced, like slice-wise shimming, then you can't input that in the scanner in the kind of traditional way. You'd be able to adjust those the gradients that you want to adjust through a sequence. So you'd have to do some sequence programming. Yeah.
Very nice. Any other questions? If not, let's thank our speaker again. Good job. Very educational.
Awesome.
Kill the feed.
You know,